plus square root of p or minus square root of p, where p denotes the transmission power, and this is a BPSK. Remember we said this is a BPSK modulation, and n is the additive wide Gaussian noise. This is the additive wide Gaussian noise of variance sigma square, and we said the probability of bit error, or which is also denoted by bit error, the bit error rate of this system, that is equal of square root of p divided by sigma square, right? So it is q of square root, which we also said can be approximated as, that is approximately equal to a half e to the power of minus half p sigma square. Fine, that is also equal to half e to the power of minus half p over sigma square, which is nothing but, since p over sigma square is SNR, that is half e to the power SNR. Fine. Now just to remind us of ourselves of this calculation again, remember last time we calculated what is the SNR. So we asked the question, what is the SNR what is the SNR required for a bit error rate of 10 to the power of minus 6. Does anyone remember what is the SNR? What is the SNR required for a bit error rate of 10 to the power of minus 6? We calculated this value. What is the SNR required? Can anyone respond on what is the SNR required? Can any college? Can you respond with the answer? What is the SNR value that we calculated last time for bit error rate 10 to the power of minus 6? Remember, this is an AWGN channel. This is AWGN channel, where AWGN stands for additive wide where AWGN stands for additive wide Gaussian noise. Can anyone remember? Yeah, 14.19 dB. I'm getting the answer from VCAP. Yeah, thank you. That is 14.19 dB. That is 14.19 dB. Just to reinforce this idea again, let us now calculate it for a slightly different value. Let us see what is the SNR required. Can someone again follow the same procedure? What is SNR for bit error rate equal 10 to the power of minus 7? Someone just answer this one. What is the SNR required for bit error rate equals 10 power minus 7? That is, we have half e to the power of minus half SNR equals 10 to the power of minus 7. I am asking what is the SNR required? What is the SNR value? I hope everyone can hear me. What is the SNR value required? Can all of you, can you compute this value? What is the SNR required for a bit error rate of 10 to the power of minus 7. What is the SNR value that is required for a bit error rate of 10 to the power of minus 7? Anyone? Anyone has the answer? Okay, both of the, I think we and LF, both of them are saying on channel, the bit error rate decreases exponentially. It decreases an exponential rate of decrease is a very fast decrease. Remember it, look at it, it is decreasing as e to the power of minus SNR, or rather e to the power of minus half SNR. So the bit error rate in an additive wide Gaussian noise channel, it is decreasing exponentially, right? So it is decreasing exponentially. So this is the bit error rate for an additive wide Gaussian noise channel, and is decreasing exponential, and this is the bit error rate that we calculated. This is the bit error rate for a BPSK system, that is a binary phase shift keying system. And remember, this binary phase shift keying system, this is not the only system, there are several other modulations possible, and the bit error rate for other modulations can be computed similarly. Alright, we are not going to go into the details of that, but in the textbook, the textbooks that I have referred, there are bit error rates for other kinds of modulation. For instance, you have Emery QAM, that is quadrature amplitude modulation, Emery PSK, that is phase shift keying modulation, Emery phase shift keying modulation, and also you have differential phase shift keying, minimum phase shift keying, and so on. So there are several modulations. The bit error rate expressions for all these modulation schemes can be computed, and they are available in the text. Now my main idea now is to basically compare this performance of the AWGN channel, that is in a traditional channel without multipath propagation, and compare this bit error rate performance of the AWGN channel with the bit error rate in a wireless communication system, that is a wireless communication system with multipath propagation. Alright, I hope that is clear to everyone. Anyone has any questions? If any college has any questions, prompt me now. I will just wait for a couple of seconds. If you have any questions, let me know. Is the calculation of bit error rate clear to everyone? For an AWGN channel, is the calculation of bit error rate, is that clear to everyone? If you have any questions, let me know. Because now we are going to go to the bit error rate with respect to a wireless communication system. Yeah, RVCE, I'm getting a question from RVCE. Go ahead, please. RVCE, do you have a question? Okay, there is no question. Alright, so hopefully everything is clear how we computed this bit error rate in an additive wide Gaussian noise channel. Now what I'm going to do is I'm going to go to the wireless communication system. So now I'm going to compute the bit error rate of a wireless communication system. So next on the agenda is basically we have to compute bit error rate of a wireless communication system, and more specifically when I say wireless communication system, of a relay fading. Now let us say we consider a relay fading wireless communication system. This is the transmitter and this is the receiver, this is the transmitter. And this is the receiver, also they are denoted by TX and RX. I have a wireless communication link with fading channel H. Therefore, my received symbol is Y is equal to, now because I have fading channel coefficient, it is no longer X plus N, but it is HX plus N. For instance, if I go to my previous system model, I said here I said Y is equal to X plus N. Everyone can see that Y is equal to X plus N. However, here for a fading communication, the channel is multiplied by the fading coefficient. Remember, we also said this is the Rayleigh fading coefficient. This is the Rayleigh fading channel coefficient, right? So Y is equal to Hx plus N. This is the Rayleigh fading channel coefficient. Remember, the Rayleigh fading channel coefficient is a channel coefficient. It's a complex channel coefficient, that is H is equal to A e to the power of j phi. Can someone tell me what is the distribution of the amplitude A and also the gain G? Does anyone remember what is the amplitude A? What is the distribution of amplitude A? And what is the distribution of the gain G of the Rayleigh fading channel coefficient? Anyone, can you prompt me on chat what is the distribution of the fading coefficient of the amplitude A and the fading coefficient G of the Rayleigh fading channel? Alright, so VCAP, I'm getting the answer, that is no. PSGCT, I'm asking the amplitude. Amplitude is not uniform. The amplitude is 2A, that is correct. 2A e to the power of minus A square. Can someone tell me what is the distribution of the gain? Can someone tell me what is the distribution of the gain G? What is the distribution of the gain G? The distribution of the gain G, that is correct VCAP, it is e to the power of minus G. That is an exponential distribution. So the amplitude is a Rayleigh distributed random variable, that is 2A e to the power of minus A square GECT, and thank you, we got the answer. That is, and the distribution of the gain is e to the power of minus. Now let us think a little bit about this communication system. Let us think a little bit about this system. See, now I have, let me write it a little bigger so that everyone can, I have Y is equal to Hx plus N. Let us go back to our BPSK system where X is equal to either plus square root of P or minus square root of P. Noise N is equal to, N is Gaussian, with variance sigma square. My question is, what is the SNR now? How has the system changed? What is the SNR of this fading channel system? What is the SNR of this? My question is simple. What is the what is the SNR of this feeding channel? What is the SNR of this feeding channel? What is the SNR of this? See, look at this. In this fading channel, what is the signal? The signal is, this is the signal part. What is the SNR? By that I mean, what is the receiver? SNR at the receiver. What is the power at the receiver to the noise? Can someone tell me what is the SNR at the receiver? Let me qualify this. SNR at the what is the SNR at the receiver? Can someone tell me what is the SNR? What is the SNR at the receiver in this system? Can someone think about, can all colleges, can you think about this? Can you prompt, someone prompt the answer? What is the SNR at the receiver? How is the system changing? What is the SNR? Yes, correct. Signal power by noise power. But what is, that is what I'm asking. What is the signal power? What is the noise power? Can someone tell me what is the signal power? What is the noise power at the receiver? What is the signal power? What is the noise power? So if you can see, basically the signal, this is H times X, and the noise is the same. What is happening is the signal H is getting multiplied by X. Correct. So PSGCT is so SNR is signal power. What is the signal power? Signal power is H times X. Signal is H times X. So signal power is, so let me write it. Signal power is, what is signal power? Signal power is expected value of magnitude H square into magnitude X square, which is basically magnitude H square into expected value of magnitude X square. But what is expected value of magnitude X square? Can someone prompt me what is the expected value of magnitude X square? What is the expected value of magnitude X square? What is the expected value of magnitude X? That is P, that is the power P, that is correct. Therefore, this is equal to magnitude H square times P. Magnitude H square is nothing but G, so I can also write this as G times P, right? Everyone can see it. I can also write it as G times P. Fine. So Y is equal to Hx plus N. Y is equal to Hx plus N. I have received power, SNR at receiver, or signal power at receiver, this is signal power at receiver. What about noise power at receiver? Noise power at receiver is equals sigma square. Therefore, now in the fading wireless channel, of course this magnitude h square, that is nothing but g. So this is also g times p. Therefore, the new SNR at the receiver, SNR at receiver, that is g times p over sigma square. So this is new SNR at receiver is g times p over sigma square. So what was previously p over sigma square, that was the SNR which was previously p over sigma square, because it was y is equal to x plus n. Now because of the fading channel coefficient, the received signal power also depends not only on the transmitted power p, but it depends on the gain of the wireless channel, or the power gain of the wireless channel g. Therefore the SNR at the receiver is GP over sigma square. Now for this SNR GP over sigma square, can someone tell me what is the bit error rate? Do we need to go do all the calculation, or can we intelligently use some earlier calculation or some earlier formula to basically derive what is the bit error rate of this system? The SNR is G times P over sigma square. Therefore, can someone tell me what is the bit error rate? My question is, what is the bit error rate for this system? What is the bit error rate of this system? Let me also give you a hint. Let me make it a little more clearer. What is the bit error rate of this system as a function of the fading channel gain G? That is, for a given gain G, what is the bit error rate of this system? Can someone tell me what is the bit error rate of this system for a given gain G? What is the bit error rate? Can someone tell me what is the answer? What is the bit error rate of this system now? And I'm also giving you a hint. We don't need to go through all the we don't need to go through the entire procedure that we went through earlier. We can simply give an expression for the bit error rate of this system. And what is the bit error rate of this system? The SNR is GP over sigma square. Yeah. Can someone also respond? Someone else, can some other college also respond? Think about it. Can someone also prompt the answer? Can someone else think about it? What do you think is going to be the probability of bit error for an SNR of GP over sigma square? When we look at the earlier expression we have for an AWGN channel, that is q square root of q square root of p over sigma square. Can someone tell me what will the probability of bit error be in this new channel? What is the probability of bit error? Okay, I think let me proceed. Since we have the received SNR is P over sigma square, that is Q square root of P over sigma square. So the SNR is G times P over sigma square. The bit error rate, I hope everyone can see, it is simply Q times square root of G P over sigma. Correct. I'm getting the answer from DCR, you also gets correct. So it's Q times square root of GP over sigma square. So the bit error rate simply SNR has because of the fading nature of the channel, the SNR has changed. Therefore, the bit error rate is Q times square root of GP over sigma square. So the bit error rate in this fading wireless channel, bit error rate equals Q times square root of G P over sigma square. We know q of x is equal to half e power minus half x square. So this is also basically I can also write this as half e to the power of minus half e over sigma square, right? Fine. This is also a half e to the power of minus half gp over sigma square. Now this is the SNR as a function of the random variable g. Remember, this is SNR, or this is bit error rate as a function of the random variable. Therefore, to compute the average bit error rate, I have to average with respect to the distribution of g. Therefore, to compute the average bit error rate, we have to average with respect to the distribution of g. That is, the distribution of G is e to the power of minus G. Therefore, see, what we are saying is the following. This bit error rate, let me go back to this over here. This bit error rate expression, this is basically, this is a function of the parameter G, right? And this is a fading channel coefficient. Remember, this is the fading channel gain. This is the gain of fading. This is the gain of the fading channel. This is continuously changing. This is a random variable, right? Therefore, to compute the average bit error rate, since G is a random quantity, I have to average with respect to the distribution of G, right? And the distribution of G is e to the power of minus G, right? Everyone get that? So now I'm going to compute the average bit error rate. Therefore, average bit error rate, average bit error rate equals integral 0 to infinity the bit error rate as a function of G, that is half e to the power of minus half G times P over sigma square multiplied by the distribution, that is e to the power of minus G P, right? Okay. So what am I doing here? I have the bit error rate, which is a function of G. This is a function of G. This is the distribution of G. This is the distribution of G. So I am multiplying this bit error rate. So I am multiplying this bit error rate, which is a function of G, with the distribution of G. I am taking the product dg and then I am averaging, basically integrating from 0 to infinity. So therefore I have 0 to infinity r e to the power of minus G into 1 plus r P over sigma square times dg. Fine. Can someone now calculate the value of this integral, that is half e to the power of minus G 1 plus half P over sigma square d. This is a simple integral. Can everyone can see this? Can someone compute this integral? What is the average bit error rate? So this, my claim is this integral. This is the average bit error rate. Can someone compute what is the value of this integral? Half e to the power of minus G 1 plus half P over sigma square dg. Can someone calculate the value of this integral? What is the value of this integral? Can someone calculate what is the value of this integral? Can you prompt me on chat, the messenger? So all colleges, please compute the value of the integral. Can you calculate the value of this integral? This is a simple integral. This is half e to the power of minus G 1 plus. Alright, PSGCT, I'm getting the answer. That is correct. VCAP also I am getting the answer correct. Can someone else also prompt me the answer? Any other college also has the answer? PSGCT has already replied, VCAP has already replied. I think both of them have the correct answer. Can someone also reply what is the answer to the above integral? Remember, look at this. This is of the form. Basically, this is, if you look at this, this is of the form integral. This is of the form integral e to the power of minus ax dx. Basically, this is the form e to the power of minus ax dx from 0 to infinity, where a is equal to 1 plus half p over sigma square. DCRU also I am getting the answer, that is half, that is 1 plus half p over sigma square, correct. So this basically you can see this integral is nothing but half 1 divided by 1 plus half e over sigma square e to the power of minus g, that is I am first evaluating the indefinite integral half e over sigma square, in fact minus 1 between the limits 0 to infinity. Of course at infinity e to the power of minus g, infinity is 0. At 0 e to the power of minus g times 0 is 1. Therefore 0 minus 1, that is minus 1. And therefore this net integral, this is basically GIT also I am getting the answer, thank you. So the net answer is basically that is equal to 1 over half 1 over 1 plus half e over sigma square, which is equal to half 1 over 1 plus half SNR, where SNR is equal to, and this is the transmit SNR. Remember there are two SNRs in the system, one is the receive SNR, one is the transmit SNR. We can think of E over sigma square as the transmit SNR. Okay. So what we are saying is the bit error rate of this fading wireless communication system, the bit error rate is, this is the average bit error rate of the fading wireless communication system. This is the average. This is the average bit error rate of the fading wireless communication system. Alright, so everyone can see this. This is the average bit error rate of the fading wireless communication system. Now we'll talk a little bit more about this, but first we will compute the same. We will go back again similar to the AWGN scenario. Let us compute what is the SNR required for a bit error rate of 10 to the power of minus 6. So BER equals, so basically 10 to the power of minus 6 is equal to half into 1 divided by 1 plus half SNR. Can someone now tell me what is the SNR required to achieve a bit error rate? What is the SNR required to achieve a bit error rate of 10 to the power of minus 6? What is the bit error rate? What is the SNR required to achieve a bit error rate of 10 to the power of minus 6? What is the bit error rate? What is the SNR required to achieve a bit error rate of 10 to the power of minus 6? Let me type the question also in the chat window to all the colleges. What is the SNR required to achieve a BR of 10 to the power of minus 6. In fact, achieve an average BER of 10 to the power of minus 6 in the Rayleigh fading. So what is the SNR required to achieve a bit error rate of 10 to the power of minus 6 in the recap? I am getting the answer. Can you give the answer in dB? Can you give the answer in dB please? Not the linear answer. Can you give the answer in dB? Okay, I am getting the correct answer from recap. PSGCT also I am getting the correct answer. Can anyone else respond? DCRU also I am getting the answer. Can anyone else respond? Very good. Several people are giving, LNMIT also giving me the correct answer. Very good. Can someone else also respond? One more college. This is simple question, right? This is SNR, BER is 10 power minus 6. I'm getting the answer from VCAP, PSGCT, DCRU, LNMIT all have responded. Very good. I've got the correct answer. Can someone else respond? One more college. Yes, RVC is also giving me the correct answer. Very good. Thank you. So the answer is, as you can see here, I have SNR. So basically simplifying this, I get 1 plus half SNR. TKMKL also give me the correct answer. Thank you. 1 plus half SNR is equal to 1 divided by 2 into 10 power minus 6, right, which is basically, so which means SNR is equal to 5 into 10 power 5 minus 1, right. So SNR is equal to 5 into 10 power twice of this value, and dB SNR in dB is equal to 10 log 10 of this value, which is 10 to the power of 6 minus 2, and this value is equal to, several have responded, this value is equal to approximately, 60 dB. In fact, let me give you a better way to do this. See, at high SNR, when SNR is very high, if I look at this term, when SNR is very high, if I look at this term, I can neglect this 1 in comparison to the half SNR. Therefore, at high SNR, this is approximately equal to a half 1 over half SNR is equal to basically 1 over SNR. Alright, everyone can see that. Let me write that simplification again. At high SNR, BR equals half 1 over 1 plus half SNR, which is approximately equal to half times 1 over half SNR at high SNR, which is equal to 1 over SNR. So therefore we have 10 to the power of minus 6 is equal to 1 over SNR, and therefore SNR is equal to 1 over 10 to the power of minus 6 is equal to 10 to the power of 6 is equal to 60 dB SNR. Now can someone tell me what is the major change? So we have seen that SNR required for 10 to the power of minus 6 is 60 dB. This is the SNR. Can someone tell me now what is the major change in comparison to the AWGN channel? So now we have SNR is equal to 60 dB. If you go back to the AWGN channel, Remember, if we go back to the AWGN channel, I had SNR of, what was the SNR? SNR was 14.19 dB. I hope everyone can see me. What is the major change? Can someone tell me what is the what is the what is the major change? What is the major in comparison to a simple digital communication AWGN channel? That is, what is a comparison to a simple channel which is a AWGN channel in which there is no fading or in which there is no multi-path propagation? MIT, I am getting the answer. So wireless, correct, correct. Can someone else respond? What is the answer? What is the, what do you see? What is the SNR is not improved? More transmit power is needed. PSG college also getting the correct. As you can clearly see, SNR for AWGN, that is approximately, for AWGN SNR was approximately 14 dB, but now for wireless SNR is 60 dB, right? So you require a much higher SNR in a wireless communication system, or wireless communication SNR required is 60 dB. So basically you require, if you look at it in the linear terms, in AWGN SNR is 14 dB in dB terms, in wireless it is 60 dB. Therefore a significantly high transmit power is needed in a wireless communication system. This implies that a significantly high transmit power is needed in, this implies that basically a significantly high transmit power is needed in a wireless communication system, right? Because in an AWGN channel, the SINR required is 14 dB. However, in the wireless communication system, the SINR required is 60 dB. So the performance of the wireless communication system is very poor. That is because even at SINR required at 60 dB, it is only 10 to the power of minus 6. Whereas in an AWGN channel, the SNR required is only 14 dB. And that arises because if you look at the wireless, if you look at the AWGN system in an AWGN channel, in AWGN, the bit error rate is decreasing as half e to the power of minus half SNR. It is decreasing exponentially. But in a wireless communication system, this is 1 over SNR. You can clearly see what we had written previously. In a wireless communication system, it is only decreasing as 1 over SNR. That is, it's only decreasing as 1 over SNR. This is a very slow decrease, very slow compared to exponential, which means the wireless communication system, the bit error rate is very high. Wireless communication has a very high bit error rate. This is due to the fading nature of the wireless channel. This is due to the, what is this due to? This is due to the This is due to the feeding nature of the this is due to the feeding nature of the wireless channel. So in a wireless communication system, the bit error rate is very high. This is due to the feeding nature of the wireless channel. For instance, let us consider for instance, we have already seen that basically at SNR of 60 dB, the wireless communication system bit error rate is, for instance, let us take another example. Let us take an SNR of 10 dB. SNR of 10 dB. SNR equals 10 dB. Therefore, what is the linear value of SNR? Linear, that is 10 log 10 of SNR equals 10, implies SNR equals 10. At SNR equals 10 for AWGN, what is the bit error rate? I'm sorry. SNR equal AWGN bit error rate is half e to the power of minus half SNR, that is half e to the power of minus 10, that is half e to the power of minus 5. Can someone compute this value? And also for wireless, for relay fading channel, bit error rate is 1 over SNR, that is equal to 1 over 10, that is equal to 10 to the power of minus 1. Can someone compute this value? What is this value? Half e to the power of minus 5. What is this value? Can someone prompt me on the messenger? What is the value? It is 3.3 into 10 to the power of minus 3. VCAP is giving me the answer 3.33 into 10 to the power of minus 3. So as you can see, wireless communication system has only 10 to the power of minus 1, while in AWGN it is 3 into 10 to the power of minus 3. So bit error rate in AWGN channel or a channel without fading is much lower. So bit error rate in wireless channel is much higher due to fading. So bit error rate in wireless channel is much higher in fading. Okay, I'm getting a request to do a recap from the beginning of this class. This is from MIT. Yeah, I think we are at 9 o'clock. We are already at 9, so let me just do a quick recap. I think we have to close the class in about 1 or 2 minutes. So see, we have a y is equal to x plus n. This is an AWGN channel. We said in AWGN channel bit error rate is half e to the power of minus half SNR. Therefore, we calculated this earlier. Bit error rate of 10 power minus 6 SNR required is 14.19 dB. Now when we come to a relay fading channel, we said relay fading channel y is equal to hx plus n, where h is the relay fading channel, and amplitude of h is a, magnitude is a, and gain, that is a square, is equal to g. Therefore, we said signal power is g times p, that is magnitude h square times p, g times p, and therefore the SNR at the receiver is gp over sigma square, which is, and therefore bit error rate is q of square root of gp over sigma square, which is approximated as half e power minus half gp over sigma square. Now when I average this half e power minus half gp over sigma square, when I average it over the gain e to the power minus g, that is to average, because g is a quantity, I have to multiply by the gain and average with respect to this, I get the expression I get, you can go through this, the expression I get is basically half 1 over 1 plus half SNR, right, where SNR is equal to P over sigma square. This can be approximated as 1 over SNR. Therefore what we said is, for a bit error rate 10 power minus 6, we approximately need 60 dB. For a bit error rate 10 power minus 6, we approximately need 60 dB, because bit error rate is decreasing only as 1 over SNR for a wireless communication system. In an AWGN system, bit error rate decreases, it decreases exponentially. Bit error rate decreases exponentially. In wireless system, it only decreases as 1 over SNR. We have done another example in an AWGN. In an AWGN, the bit error rate is half e to the power of minus 5, and in wireless bit error rate is 10 power 10 e power minus 1. I am getting request to show the first please to slide. That is why I am saying all of you, please, you have to log in promptly at 8 o'clock, please, because it is not possible for me to go over all the aspects that are done in this thing. I am seeing several colleges, they are logging in slightly late, so they are missing the initial part of the classes. Also, I would like to remember all the classes that what we are going to do from now on is we're going to be very a little bit more serious and intense, right? So you have to answer all, you have to understand all of the previous concepts so that you understand what is going to be done in the future. All right. So please log in promptly at the correct time, that is at 8 o'clock, so that we can start the class on time, and also it will make it smoother for all of you, because if you miss the couple of initial slides, then it is going to be very difficult to catch up later. So I request all colleges kindly make sure, kindly make appropriate arrangements so that everyone is here by 8 o'clock. Thereby no one is missing what is not there, what is there in the initial slides. All right, please log in at if possible, please log in earlier, 7:30, 7:45, so that all your video audio issues are resolved. If you log in at 8 o'clock, then it will be difficult, there will not be enough time to resolve the video audio issues. Alright, so kindly make appropriate arrangements so that all of you are here promptly, because otherwise it will be very difficult to follow the later parts of the lecture if you miss the initial parts. Alright, so please, I think again, if you have any questions, send these questions to me offline. Also please go over the lecture notes again. Right now I have to close the session. Thank you very much. Thank you very much. So I think we are now getting into a very, we are now getting into some of the more interesting aspects. That is, we are looking into the better rate of wireless communication system. Now we are going to talk about even more interesting aspects. What happens when you have multiple antennas? What happens when you have multiple fading channels? How does the bit error rate improve? What are the problems in wireless communication systems? What are the different wireless communication technologies? Right? All right. Okay. So I think KNMU, I think I'm getting earlier lecture. All the lectures are recorded. I'm recording all the lectures. Kindly, if we are not able to access the recorded lectures, kindly resolve the issue with technical support. Alright, all the recorded lectures along with the notes are available on AView. Alright, I am recording all the lectures. Okay. Alright, thank you everyone for your attention. I hope this is interesting.